Thursday, 6:12 a.m. A mother waits beside a rattling window unit while her child lies awake beneath a damp towel. We keep burning electricity and leaking refrigerants just to move heat outside. The cooler is now part of the heat problem. The apartment trapped yesterday's heat. Outside, the city wakes inside the machine's exhaust. That dependence is scaling fast. The International Energy Agency projects residential air conditioning will need 700 terawatt-hours more electricity by 2035, roughly one large industrial country's annual consumption, and triple the growth expected from data centers. During 2025 heat waves, electricity peaks rose 25% above off-season levels in France and 90% in New York. When everyone cools simultaneously, this family's relief becomes costlier. Researchers at Hong Kong University of Science and Technology, known as HKUST, and Cambridge spin-out Baracol, are testing solid-state caloric cooling. Elastocaloric, electrocaloric, and barocaloric systems move heat by applying force or voltage to eliminating compressors and chemical refrigerants. But what must those solids endure? The real question is whether a solid can outperform gas cycle AC at room temperature, survive constant repetition, and remain cheap enough for this family's window. To understand the wall, follow heat through ordinary AC. A compressor squeezes refrigerant vapor, making it hot. Outdoor coils release that heat. The refrigerant expands, becomes cold, and absorbs indoor heat. After a century of refinement, this vapor compression cycle is near its practical thermodynamic ceiling. It still relies on hydrofluorocarbons, HFCs, refrigerant gases often thousands of times stronger than carbon dioxide at trapping heat. Traditional AC contributes roughly 2 to 3% of global greenhouse emissions. Imagine rapidly bending a metal strip until it warms your fingers. Certain solids release heat when stressed, then absorb heat as they relax, like mechanically charged heat sponges. That is when the refrigerant stops being a fluid. Nickel titanium, or Ni-Ti, is a shape memory alloy, a metal whose atoms switch arrangement under stress, then return. Stretch it, and it releases heat. Carry that heat outside. Relax it, and it absorbs heat from the room. Efficiency is measured by coefficient of performance, or COP. Cooling delivered divided by energy consumed, like distance traveled per liter of fuel. Standard vapor compression reaches about 3.2. Elastocaloric theory reaches 12, almost 4 times higher. CivilizationX tracks real constraints and numbers. Stay for why a COP of 12 still fails outside simulations. That potential makes the material itself the machine. Solid-state systems may reduce energy consumption by 20 to 47%, between 1/5 and nearly half. HKUST demonstrated a 1.2 kilowatt elastocaloric system, roughly room-scale thermal power, with a 75 Kelvin temperature rise, equivalent to a 75 degrees Celsius difference. Now the floor drops. The solid refrigerant must be tortured millions of times. Repeated stress creates microscopic fractures. Eventually, performance fades or the alloy snaps. Without volatile gases or complex compressors, mature systems might last almost indefinitely, but only if fatigue is solved. AI attacks that search problem through inverse design, define cooling performance, durability, and cost, then search backward for suitable crystal structures. DeepMind's genome identified 380,000 predicted stable crystals. External laboratories synthesized 736, accelerating discovery by an estimated 10 to 100 times. EnergyGnome then filtered databases to 38,500 candidates for energy technologies. Mater AI received 500,000 graphics processor hours on Britain's Isambard AI supercomputer, equivalent to one processor running for 57 years, to calculate atomic behavior. Models can also predict ZT, a score measuring how effectively a material converts heat differences into electricity. Autonomous laboratories now combine AI planning with robots, achieving about 71% synthesis success, roughly 7 viable recipes from every 10 attempts. But the digital search concealed a brutal filter. Many predicted crystals appear stable because density functional theory, software that calculates electron behavior, often models perfect structures near 0 Kelvin or absolute zero. Real materials face room temperature disorder, defects, manufacturing limits, and entropy, nature's tendency toward mess. Many candidates therefore fail after synthesis. Current devices also deliver less cooling per unit of size than commercial AC and require expensive specialty alloys. Room-scale elastocaloric and barocaloric prototypes may remain 2 or 3 years away. The first installations may therefore appear in laboratories or premium buildings, not heat-trapping rental apartments. Barocol has raised $10 million to develop pressure-driven cooling materials. Meanwhile, coatings that reflect 97% of sunlight can lower surfaces by 7 degrees Celsius, reducing the load solid-state machines must handle. The practical path is layered, not instantaneous. Back at sunrise, the window unit keeps rattling because elegant laboratory physics has not yet become an affordable appliance. Can researchers manufacture a high-performance room temperature alloy that survives hundreds of millions of cycles and remains cheap enough for renters? The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem. Stay with CivilizationX.